Now we're moving into 6.3, trigonometry of arbitrary angles. In the previous section we talked about trigonometry, yes, but the angle was always an acute angle. The reason is because we were confining ourselves inside the right triangle, so the angle of consideration was always an acute angle. Now, what if we consider obtuse angles or negative angles or even worse? Well, in that case, we cannot inscribe that angle inside the right triangle anymore. So we have to go back to the general definition of the radian angle in the circle of radius r. So let us do that. Let's begin with a circle centered at the origin with the radius r. And that can be written as x squared plus y squared equals r squared, and that's coming from the Pythagorean theorem. X is horizontal, y is vertical, and r is hypotenuse, so x squared plus y squared has to be equal to the hypotenuse squared, r squared. What if x and y are negative? In this particular case, x and y are both positive because they're coming from the point x comma y is coming from the first quadrant. But what if you have something like this? In this case, x is negative, y is positive. Does it matter? No, because we are going to square them anyway. So negative becomes positive, so nothing matters. In some other situation, in this particular case, x is positive, y is negative. Again, no problem. Now, how do we define the angle or the radian measure of the angle? We define it as the counterclockwise arc length divided by the radius, and that is always a constant as long as we have the same terminal ray, as you can see in this visualization. And if we move clockwise, then that's negative angle. Consequently, we have this kind of arc length formula. As a matter of fact, angle was defined by the counterclockwise direction of the arc length over the radius. But if you throw away the direction and then take just magnitude only, then theta is equal to s over r, arc length over radius. Consequently, s equal to r theta. Another formula that I'd like to remind you was area of a sector is 1/2 r squared times theta, and that's something we discussed in 6.1. Okay, that was a quick review, and let's talk about trigonometric functions of arbitrary angles. We begin with a circle of radius r centered at the origin, the same circle we saw before, and we define sine, cosine, tangent, cosecant, secant, and cotangent as follows. Sine of theta is defined by y over r, vertical over the radius. Cosine of theta is defined by x over r, horizontal over the radius. And tangent of theta is y over x, vertical over horizontal. Cosecant, secant, and cotangent are their reciprocals, as you can see here in the definition and also in the visualization. In this particular case, the angle theta is an acute angle, so we can inscribe the central angle inside a right triangle, as you can see here in this visualization in the lower left hand side corner. So we have the same situation as in the previous section. Now what if we go beyond the acute angle? Well, I was lucky. I got second quadrant right away. In this case, the angle theta exceeds pi over 2, but does not reach pi. So it is between 90 degrees and 180 degrees in terms of the DMS measure. In this case, well, sine, cosine, and tangent are defined exactly the same way. However, x is negative this time. Y is positive, yes, because we are going up, but x is negative because we are going to the left-hand side. So what we have, sine is positive, y over r, both are positive. Cosine is negative, x is negative, r is always positive, so that's negative. Tangent is negative too, y over x. Numerator is positive, but denominator is negative. And in this case, do we have right triangle? Yes, we do. We have right triangle, except that the angle is not inscribed inside the right triangle, but it goes outside, and the right triangle is actually helping us to consider. And we can use geometry from triangles, of course. Now, what if we go to the third quadrant? Let's run this program again. Well, this is randomized. Okay. So I was lucky. Again, in the second try, I ended up with the third quadrant. In this case, both x and y are negative. So sine and cosine are both negative. R is the radius, so it's always positive. X and y are negative in this case. So sine and cosine are both negative. Tangent, on the other hand, is positive because both numerator and denominator are negative. Y of x is positive. And the right triangle, as you can see here, will help us finding out the trig values using some geometry. Okay, I'd like to guess. Okay, I got it. What if we get something? What if we get the terminal angle? The terminal point in the fourth quadrant. In other words, the angle theta exceeds 3 pi over 2, but does not reach 2 pi. In that case, we get the fourth quadrant, and x is positive, y is negative. So what do we get? Cosine is positive, but sine is negative. Tangent is also negative. In terms of those signs, we have this summary: a smart trig class. Starting from the first quadrant, all positive, sine is positive, tangent is positive, and cosine is positive. In this particular case, we get fourth quadrant as a terminal point. So in this case, x is positive, y is negative, so only cosine is positive, and the other standard trigonometries, sine and tangent, are negative. If I run it again, okay, we ended up with third quadrant. In this particular case, both x and y are negative, so y over x, tangent, is positive, the others are negative. Well, same argument applies for second quadrant too. So we end up with a smart trig class. All positive, sine is positive, tangent is positive, cosine is positive. Our textbook calls it something like this: all student take, kind of like that, but I don't like it very much. I mean, we still have to we'll still have a long way to go to calculus, so it doesn't make too much sense to me. I like a smart trig class. Okay, we talked about the trigonometric functions for arbitrary angles, and we talked about the signs of trigonometric functions. Let's talk about some magnitudes of well-known trigonometric functions at basic angles. Well, that's summarized in this table, actually in this diagram, as a matter of fact. Cosine of theta, sine of theta are summarized here in this diagram, and the theta values are specified both in radian measure and the DMS measure. For example, if you're interested in 30 degrees or pi over 6, the first coordinate is cosine and the second coordinate is sine. So cosine of 30 degrees is square root of 3 over 2. Sine of 30 degrees is 1/2. If you're interested in, for example, tangent of 3 pi over 4, in that case, tangent is y over x, isn't it? So you have to take the ratio of second coordinate over the first coordinate. So what do you get? Square root of 2 over 2 over negative square root of 2 over 2. You're going to get -1. You can read everything from this trig diagram. This is actually a grand summary, and I'm going to post this one, this diagram, as a separate JPEG file on the blackboard, so that you can print out and then you can refer to it. Okay, that was a summary, but I'm still interested in how in the world we got those values. Well, This is a review. We talked about these kind of things before in acute angle trigonometry, but here we go again. We have two basic triangles to consider. One is 1 square root of 3, 2 triangle, as you can see here, and that's ultimately coming from our equilateral triangle of side 2. And we take a bisector, bisecting line of the top angle, then by symmetry, that's bisector, that's bisecting line of the top angle, bisects the bottom side perpendicularly. So we have 1 and 1 in left hand side and right hand side, and we have a right triangle on the left hand side and right hand side. We have green and red. And then we use Pythagorean theorem to find out the height. That'll turn out to be square root of 3. We have already done that in the previous section, so I can refer to that. And that's something we're going to be using. The other triangle is going to be 1 square root of 2 triangle. So that is an isosceles right triangle. Again, we get square root of 2 from the Pythagorean theorem. And in case of the first quadrant, we have something like this. First, we have degenerate triangle, just a line segment. Vertically, we go nowhere. Vertical is 0, so sine is 0. Horizontally, x is equal to r, so x over r is 1. Tangent is y over x, so it's 0 over x, so that's 0. Now we have a basic triangle here. We have 30 degrees, so just slip in one of the basic triangles, 1 square root of 3, 2 triangle, and we get these trig values. What if we have 45 degrees, pi over 4? In that case, it's going to be the other basic triangle, 1 square root of 2 triangle, and consequently we have these trig values. What if we have 60 degrees now, pi over 3? That's going to be the first basic triangle again, only positioned differently. Finally, if we have pi over 2, 90 degrees, then we have a degenerate triangle again. It's a line segment. Sine is 1 because vertical is the same as the radius. Y is equal to r, so y over r is 1. Cosine is 0 because x is 0. Horizontally, we go nowhere. Tangent is going to be undefined because it is y over x, and denominator x is 0. Now what if we go beyond the 90 degrees and go over to an obtuse angle? Do we have more triangles to consider? Actually no, we still have the same basic triangles, only positioned appropriately like this. What if we have 3 pi over 4? Still the same basic triangle, 1 square root of 2 triangle, only positioned in a strategical fashion. Same old, it's the same basic triangle positioned appropriately. The same kind of logic continues for the third quadrant. It's the same basic triangle again. Ditto, the same basic triangle, only positioned in a strategic fashion. So all these can be deduced from the same basic triangles. All you have to worry about, or all you have to be careful about, is a sign. And we already talked about the sign, a smart trig class. In short, we just covered all the trig values of the basic angles, which can be summarized in this trig diagram.